Welcome back. In the last 3 lectures we discussed reciprocating compressors. As you know, reciprocating compressors is one of the positive displacement type of compressors. Okay. In this lecture I shall discuss other positive displacement type of compressors. We will not go into the details, but I will briefly explain the working principle of these compressors and their typical performance characteristics. So, the specific objectives of this particular lecture are to discuss the working principle and characteristics of rotary compressors, namely rolling piston type, multiple vane type, screw type and scroll type. At the end of the lecture you should be able to explain the working principle, applications and performance characteristics of rotary compressors, namely as I have already mentioned, rolling piston type compressors, multiple vane type compressors, screw type and scroll type compressors. So, let us begin with the first type of compressor, that is rolling piston type compressor. Rolling piston type compressors is also known as fixed vane type compressor. They belong to the class of positive displacement type, as compression is achieved by reducing the volume of the refrigerant. These compressors are used in small refrigeration systems, that means up to 2 kilowatt of refrigeration capacity, and they are mainly used in domestic refrigerators or small air conditioners. Now, let us look at the working principle. Let me describe the working principle first, then I will show you the figure. In these compressors, the rotating shaft of the roller has its axis of rotation that matches with the center line of the cylinder. However, it is eccentric with respect to the roller. This eccentricity of the shaft with respect to the roller creates suction and compression of the refrigerant. A single vane or blade is positioned in the non-rotating cylindrical block. The rotating motion of the roller causes a reciprocating motion of the single vane. Okay, now let me show you the picture of it and explain. So, as I have already described, this compressor consists of a cylinder block, this is a cylinder block and a roller. Okay. Now, the axis of rotation, this is the point, the axis of rotation is eccentric with respect to the roller. However, it coincides with the center line of the cylinder block. Okay, so that is the main principle behind the operation of this particular type of the compressor. Okay, the eccentricity between the axis of rotation and the center line of the roller. Okay, and this cylinder block consists of a slot in which a fixed vane is mounted, and normally this fixed vane is spring loaded. Okay, so you have a spring loaded fixed vane, and as you can see that this type of compressor does not require a suction valve. So, you do not have any valve on the suction side, but it uses a discharge valve. So, you can see the discharge valve, but no suction valve. Now, let me explain the working principle of this compressor. Let us begin at this point A, let us say. Okay. Now, the roller is at this position, and this side you have refrigerant and this side also you have refrigerant. As the roller rotates in this direction, the gas on this side, it gets compressed, and on this side you have suction. So, that is what is seen here in picture B. Okay, this gas is getting compressed because its volume is getting reduced. At the same time, on this side suction is taking place because its volume is increasing. Okay. Further rotation of this compressor will compress the refrigerant to such an extent that this pressure will exceed the condensing pressure, discharge valve opens and the refrigerant goes out of the discharge valve. Okay. So, again here you can see that you have the suction refrigerant and here you have the discharge. Okay. And as this roller is rotating, this fixed vane will be reciprocating in this direction. Okay. And as I said, you have a spring loaded fixed vane. So, this spring loaded vane will always remain in contact with the roller, so that a point of sealing is obtained between the high pressure side and low pressure side. Okay. So, this is the working principle and it is a very simple type of a compressor. And as I have already explained, this type of compressor does not require a suction valve, but it requires a discharge valve, and the sealing between the high and low pressure sides has to be provided along the line of contact between roller and cylinder block, along the line of contact between vane and roller, between the vane and the vane slot, and between the roller and end plate. So, let me explain this once again. So, you have, as I have explained, for example, if you look at this figure, you have the high pressure refrigerant on this side and low pressure refrigerant on this side, and there are different leakage paths. What are the leakage paths? For example, refrigerant can leak like this, so that means this is one of the leakage paths, okay. And again refrigerant can leak this way, so this is another leakage path, and refrigerant can also leak in this manner, okay. That means between the gap between the slot and the vane, okay. And it can also leak from the end plates, that means perpendicular to the screen, okay. So these are the 4 leakage spots through which the high pressure refrigerant can leak back to the low pressure side. So you require sealing at all these 4 points, okay. So the leakage is controlled through hydrodynamic sealing and matching between the mating component. That means what is done is a layer of lubricating oil fills up these gaps between the roller and the cylinder block, between the vane and the roller, and between the slot and the vane, and between the end plate and the roller, okay. So this it provides lubrication, at the same time it also seals the gaps. As a result, the leakage from the high pressure side to the low pressure side is minimized. Of course, this is not enough, you also have to manufacture them very accurately, so that the tolerance is very small. That means the gap between these components or between these mating components is very small, of the level of microns, okay. This is one of the important requirements, okay. And as I said, the effectiveness of the sealing depends on the clearance, compressor speed, surface finish and oil viscosity. Close tolerances and good surface finishing are required to minimize internal leakage. Hence, manufacturing of the compressors is difficult compared to reciprocating type compressors. The mass flow rate of refrigerant through the compressor is given by, as you know, the mass flow rate is equal to volumetric efficiency into displacement rate of the compressor divided by the specific volume of the refrigerant at compressor inlet. That is what is shown in this equation. So this is your displacement rate, and this is the specific volume at the compressor inlet, and this is the volumetric efficiency. Now the displacement rate is nothing but this, okay, where n, as you can see, is the rotational speed in RPM, this is the RPM, and A is nothing but the inner diameter of the cylinder, B is the diameter of the roller, and L is the length of the cylinder block, okay. And so pi by 4 into A square minus B square L is the volume between the cylinder block and the roller, okay. If you multiply that into the rotational speed, that will give you the displacement rate, and the actual mass flow rate is nothing but the displacement rate into the volumetric efficiency divided by the specific volume, okay. That is what is shown in this equation. Now let us look at other type of positive displacement type of compressor, that is multiple vane type compressor. Let me describe this compressor first. In multiple vane type compressor, the axis of rotation coincides with the center of the roller. However, it is eccentric with respect to the center of the cylinder, okay. So there is a difference between this type of compressor and the fixed vane type of compressor. The rotor consists of a number of slots with sliding vanes. During the running of the compressor, the sliding vanes, which are normally made of non-metallic materials, are held against the cylinder due to centrifugal forces. This is very important to remember. Now let me explain the working principle here. So again you have a rotor here, this is a rotor, and you have the cylinder block, okay, and this rotor has a number of slots, okay. These are the slots of the rotor, this one, okay. So in this particular figure I have shown 4 slots, and each slot consists of a sliding vane, okay. So this is the sliding vane, this is one sliding vane, this is sliding vane. So 4 slots mean there are 4 sliding vanes. And one important thing to notice here is this is the axis of rotation, that is point O. The axis of rotation coincides with the center line of the rotor, okay. That means the shaft, rotating shaft, and the rotor are coincidental, okay. But this center of rotor is eccentric with respect to the center of the cylinder, okay. That means as I said, this O is the center of the shaft and rotor, this is O, and O dash is your center of the cylinder block. Okay. Now, as let me explain the working principle. There is an eccentricity between the axis of rotation and the cylinder block. So, when the rotor rotates like this, these vanes they will be flung out outwards. That means they will be flung outwards because of the centrifugal action. As a result, these vanes will be pressing against the cylinder block. Now, all this space is filled with refrigerant. Okay, and this volume varies as the rotor rotates. For example, you look at this cell. Okay, now this cell has this much volume. Okay, this is the volume of the refrigerant in this particular cell. So, as the rotor rotates and when this cell comes to this position, its volume is reduced. That means its pressure will increase, and with further rotation its volume is reduced further and its pressure increases further, and at some point this compressed gas will be open to this discharge port. Okay, when this is open to this discharge port, it is designed in such a way that at the design point this pressure will be equal to the condensing pressure, or it will be slightly higher than the condensing pressure, so that the compressed gas will leave from the discharge port. Okay, and you can see that at any point of time you have, for example, if you are using 4 sliding vanes, you have 4 cells which are filled with the. Okay, so this is 1, this is 2, this is 3, and here is 1, 4 cells. These 4 cells are filled with 4 refrigerant, and continuously the volume will be compressed and suction will be taking place continuously, and compression will be taking place continuously. Okay, and you can also see that it does not have either suction port or discharge port. So, number of compression strokes produced in one revolution of the rotor is equal to the number of sliding vanes. Thus, a 4-vane compressor produces 4 compression strokes in one rotation. Of course, it is not necessary that you have to have 4 vanes only. You can also have different number of vanes. For example, you can have 2 vanes, or you can also have 6 vanes or 4 vanes, like that. Normally, the 4 vanes or 6 vanes are more common. Okay, if you have 4 vanes, there will be 4 cells, and if you have 6 vanes, there will be 6 cells. Okay, and again just like your fixed vane compressor, sealing is required between the vanes and cylinder, between the vanes and the slots on the rotor, and between the rotor and the end plate. Okay, let me show this on the figure. If you look at this figure, for example, in this cell, let us say that this is cell 1. Okay, here the pressure is P1, and this is cell 2, and here the pressure is P2. Okay, so at this point of time P1 will be greater than P2. So, there is a pressure difference between this cell and this cell. So, there will be a if there is a gap, then the refrigerant in cell 1 will try to flow back to the cell 2. Okay. So, what are the leakage paths here? For example, the leakage can take place like this. Okay, that means if there is a gap between the sliding vanes and the slot, leakage can take place, and the leakage can also take place like this if there is a gap between the vane and the cylinder block, and leakage can also take place perpendicularly if there is a gap between the this roller and the end plate. Okay, so these are the 3 leakage paths through which the high pressure gas can leak back into the low pressure side. But unlike fixed vane compressor, here the pressure difference available for leakage is less. For example, let us say that at this point only the pressure is P discharge. Okay, so here the pressure will be less than P discharge, and here it will be further less than P discharge. Okay, so the pressure difference between any 2 adjacent cells is much less than P discharge minus P suction. Okay, that means the leakage rate also will be less. So, the sealing is not as critical as that in fixed vane compressors. So, that is what is mentioned here. However, since the pressure difference across each slot is only a fraction of the total pressure difference, the sealing is not as critical as in fixed vane type compressor. This type of compressor does not require, as I have already mentioned, suction or discharge valves. However, check valves are used on discharge side to prevent reverse rotation during off time due to pressure difference. Okay, so let me show the So, this one shows the constructional features of a multiple vane compressor. You can see that there is no valve on the suction side. Okay. However, a check valve, or this is a check valve or non-return valve, is used on the discharge side. Okay. The purpose of this is that during the when the compressor is off, if this valve is not there, since this pressure PD is always greater than suction pressure, backflow can take place. That means the refrigerant can flow back from discharge side to the suction side. Okay. And when this is flowing back, then this will rotate, the rotor will rotate in the opposite direction. Okay. So, to prevent this one, the check valve is used, and the check valve will allow the refrigerant flow in this direction, but it will not allow refrigerant flow in this direction. That is the purpose of the check valve. And you can see from this particular picture that there are cooling water jackets here for keeping the compressor cool. Okay, and this particular picture shows 6 vanes. Okay, 1, 2, 3, 4, 5, 6, 7. In fact, there are 7 vanes here. Okay. And since there are no discharge valves, the compressor refrigerant is open to the discharge port when it has been compressed through a fixed volume ratio depending upon the geometry. This is one of the typical characteristics of this multiple vane type of compressor. That means they have what is known as a fixed built-in volume ratio. That means as you have seen, there are no suction or discharge valves. Since there is no discharge valve, when the rotor comes to a particular position, the refrigerant, the compressor refrigerant will be exposed to the discharge port. Okay, that means the pressure becomes the discharge, it is connected to the discharge side, and the ratio between the volume at this point and of course the inverse of the ratio of the volume at this point and the volume when the slots are closed is known as the built-in volume ratio. Okay. So, all these fixed all these multiple vane type of compressors have what is known as the built-in volume ratio. Okay. Since the built-in volume ratio is fixed, which is depending upon the geometry, the built-in pressure ratio is also fixed. Okay. And this is the, let me summarize this. This implies that these compressors have a fixed built-in volume ratio, and the built-in volume ratio is defined as the ratio of a cell as it is closed off from the suction port to its volume before it opens to the discharge port. This is the definition of built-in volume ratio. Since the volume ratio is fixed, the pressure ratio Rp is also fixed, and this Rp is given by Pd by Ps, where Pd is the discharge pressure and Ps is the suction pressure. This is equal to the built-in volume ratio to the power of K, where K, as you know, is the isentropic index of compression. Since no centrifugal force is present when the compressor is off, the multiple vanes will not be pressed against the cylinder walls during the off period. That means, let us say that when the compressor is off, there is no centrifugal action. When there is no centrifugal action, these vanes will not be pressed against the cylinder block. For example, if you look at this vane, this will not be, there will be no centrifugal action. So, this will not be pressed against the cylinder block. So, due to gravity it will fall down. Once it falls down, a gap is created here. So, as a result, this high pressure gas can flow back through this gap onto to the suction side. Similarly, there will be refrigerant flow from this point, okay, and the refrigerant flow like this, refrigerant flow like this. Okay. So, that means during the off position there is a possibility of pressure equalization on the discharge as well as suction sides. As a result, high pressure refrigerant from the discharge side can flow back into the suction side, and pressure equalization between high and low pressure sides takes place. This is beneficial from the compressor motor point of view as it reduces the required starting torque. As you know very well, when pressure equalization takes place, the motor has to start against the same pressure. That means there is no back pressure acting on the motor. So, the required starting torque will be very less. Okay. So, you can use a smaller motor. This is one of the advantages of having pressure equalization. Okay. Of course, pressure equalization also has disadvantages. Let us look at what is the disadvantage of this. Whenever there is a pressure equalization, it introduces what is known as the cycling loss. Okay. And what is cycling loss? Cycling loss is nothing but the entry of hot and high pressure refrigerant liquid into the evaporator. Hence, normally a non-return check valve is used on the discharge side which prevents the entry of refrigerant liquid from high pressure side into evaporator through the compressor during off time. At the same time, there will be pressure equalization across the vanes of the compressor. Okay. That means when you are using the non-return valve, so during the off time this non-return valve will be closed, okay, this will be closed. So there will not be any refrigerant flow from this side to this side, okay, but there will be refrigerant flow across these rotors. That means pressure equalization will take place at the roller, but there will not be any pressure equalization in the overall system. As a result, this roller can rotate since the pressure equalization is there, the motor can rotate with less starting torque. At the same time, the cycling losses are prevented because this non-return valve will not allow this refrigerant liquid from the condenser to enter into the suction side. Okay, so that is the purpose of the non-return check valve. The compressors are normally oil flooded type, hence oil separators are required. As I said, you have to do the sealing is required between the various leakage paths, and normally the sealing is achieved by using hydrodynamic lubrication. That means lubricating oil is used to seal the leakage paths. Okay. So let me show this. Okay, so this shows the animation of multiple vane type compressor. You can see here that an oil separator is used, this red side. This is the oil separator, okay, and this is the oil sump, and all this orange color and here the orange color means there is a thin film of lubricating oil between the sealing paths, so that refrigerant leakage from the high pressure side to low pressure side is prevented. Okay. So refrigerant liquid, refrigerant vapor enters like this, it gets compressed, it comes out like this, okay, it comes out like this and flows out like this, and this, as I said, is the oil separator. This is the oil separator, and here oil gets separated and refrigerant vapor only will go to the compressor, and this separated oil will again come back to the oil sump through the oil return valve. Okay, so this is the principle. Of course, this picture shows a suction valve, but it is really not necessary to use a suction valve. Okay. Now let us look at the characteristics of vane type compressors. In general, vane type compressors have low mass to displacement ratio and they are also compact. As a result, they are really ideal for transport applications where compactness and less weight are important. And both single stage as well as two stage compressors are available. Single stage compressor means you can achieve evaporating temperature up to -40°C when the condensing temperature is at 60°C, and two stage compressors means they are available up to about -50°C evaporated temperature, and normally the cooling capacities at present fall in the range of 2 to 40 kilowatt, and these compressors are available for a wide range of refrigerants such as R22, ammonia, R404A, etc. And cooling capacity is normally controlled either by compressor speed regulation or suction gas throttling. I have explained what is the meaning of compressor speed regulation and suction gas throttling in the last lecture. Now let us look at the other important type of positive displacement type of compressor, that is what is known as screw type compressors. Screw type compressors can be either single screw type or twin screw type. So let us first look at twin screw type of compressor. The twin screw type compressor consists of two mating helically grooved rotors, and one is a male rotor and the other one is a female rotor. The male rotor drives the female rotor. The male rotor has lobes while the female rotor has flutes or gullies. Let me show this. The frequently used lobe gully combinations are 4, 6, 5, 6 and 5, 7. For the 4-6 combination, when the male rotor rotates at 3600 rpm, the female rotor rotates at 2400 rpm. So, let me explain this with a picture. This is a 4-6 combination, okay, and this is the male rotor, and this is the female rotor, and male rotor has lobes, okay, this is 1, 3, 4, it has 4 lobes, that is why we call this as 4, and the female rotor has 6 gullies, okay, this is 1, 2, 3, 4, 5, 6, okay, and this male rotor is the driving one and it drives the female rotor. So, this rotates in this direction. So, as this rotates in this direction, the female rotor will be rotating in this direction, and as you can see that when since this is a 4-6 combination, when the male rotor has 3600 speed of 3600 rpm, this one will have 3600, the female one will have 3600 rpm into 4 by 6, that means 2400 rpm, okay. The flow is in the twin screw type of compressor, the flow is mainly in the axial direction. Let me show this. Okay, so this is again a cut view of a twin screw compressor. This is the male rotor and this is the female rotor. Okay, so this will be rotating in this direction and this will be rotating in this direction, and suction gas enters like this, it gets compressed and it leaves the compressor in this manner. Okay, so and both the female and male rotors are housed in a housing. Okay, you have a housing. So, as you can see that the refrigerant flow is basically in the axial direction, it flows in this direction, and this is the axis of rotation. Suction and compression take place as the rotors mesh and unmesh. So, let me show the animated picture of this. You can see the animation here. You have low pressure refrigerant enters like this, okay, it is coming like this and it fills up this space, and as this one rotates, it will be carried away along these gullies and the lobes, and finally it gets compressed and it leaves the compressor in this fashion. Okay. So, basically the flow direction is in this direction. Yeah, so you can see the how the flow is taking place. The blue one is the suction gas, blue color, and the red color indicates that it is getting compressed. Okay, and you have an outer cylinder casing where these twin screws are housed in the cylinder casing. Okay, so when one lobe gully combination begins to unmesh, the opposite lobe gully combination begins to mesh. With 4 male lobes rotating at 3600 rpm, 4 interlobe volumes are compressed per revolution. That means you have 4 into 3600, that is 14,400 discharges per minute. Okay, so this depends upon the, if you have let us say 6 male lobes, then it will be 6 into 3600 discharges per minute. Discharge takes place at a point decided by the designed built-in volume ratio. That means just like your multiple vane type of compressor, here also you have what is known as a built-in volume ratio, and this built-in volume ratio depends upon the location of the delivery port and geometry of the compressor. Since the built-in volume ratio is fixed by the geometry, a particular compressor is designed for a particular built-in volume ratio. However, different built-in volume ratios can be obtained by changing the position of the discharge port using a slide valve. If the built-in pressure at the end of the compression is less than the condensing pressure, high pressure refrigerant from discharge manifold flows back into the interlobe space when the discharge port is uncovered. This is known as under compression. Okay, that means what happens is, since you have a typical twin screw compressor has a built-in volume ratio. Okay, that means the volume ratio is fixed, and the volume ratio, as we have defined in the for in case of multiple vane type of compressor, is a ratio of the suction volume divided by the volume just before discharge takes place. Since this is fixed, the compression ratio is also fixed, because you know that the compression process in general obeys an equation PV to the power of n is constant. So, when the volume ratio is fixed, the pressure ratio is also fixed. Okay, and as I said, the built-in volume ratio depends upon the geometry of the compressor. Once you fix the geometry of the compressor and the location of the discharge port, the built-in volume ratio is fixed. That means the built-in pressure ratio is also fixed. Since the built-in pressure ratio is fixed, let us say that you have some suction pressure. Let us say that a suction pressure of 2 bar, and let us say that built-in pressure ratio is 6. That means the discharge pressure will be 2 into 6, that is 12 bar. And if the condensing pressure is greater than 12 bar, let us say that condensing pressure is 13 bar. As you know, the condensing pressure depends upon the available heat sink temperature. So, it is possible for the condensing pressure to be higher than the built-in pressure. Okay, if it is higher than the built-in pressure, and let us say it is 13 bar, whereas the pressure developed in the compressor is 12 bar, then when the discharge port is uncovered, the condenser pressure is higher than the compressed refrigerant pressure. That means there will be a reverse flow, and this is what is known as under compression. Okay, you can also have the other on the other hand, you can also have a scenario where the discharge pressure at the end of compression is much higher than the condensing pressure. This is known as over compression. Okay, so that means as soon as the discharge port is uncovered, since there is a pressure difference between the condenser and the compressed gas will rush out of the discharge port. That means there will be a throttling of the refrigerant vapor at the discharge. Okay, so this is known as over compression. Both under compression as well as over compression are bad for as far as the compressor performance is concerned, because both will reduce the efficiency. This is one of the typical problems of twin screw compressor. This you can call it as a problem if you are operating the system at off design conditions, but normally the compressors are designed to operate at design conditions, and if you design the compressor in such a manner that at the built-in pressure is equal to your condensing pressure, then you get the peak efficiency. Okay, you do not have any problem, but it is possible for the compressor to operate at off design condition, then you may have either under compression or over compression. Okay. So, as I said, if the built-in pressure is higher than the condensing pressure, then the compressor refrigerant rushes out in an unrestrained expansion as soon as the port is uncovered. Both under compression and over compression are undesirable as they lead to loss in efficiency. Lubrication and sealing between the rotors is obtained by injecting lubricating oil between the rotors. A large amount of lubricating oil is injected between the rotors. The oil also helps in cooling the compressor. As a result, very high pressure ratios are possible without overheating. This is one of the major advantages of screw compressor, since they are oil flooded and the lubricating oil can carry away a lot of heat. One can go for a large pressure ratio, okay, typically as high as 20:1. That means instead of using a multi-stage compression, you can achieve a large compression ratio using a single stage screw compressor. Okay, and at the same time you can also keep the discharge temperature low, because the oil carries the heat from the compressor, so the discharge temperature of the refrigerant will not be very high. Okay. Of course, you can also use in some of the compressors, instead of using lubricating oil, people use a liquid refrigerant itself for sealing as well as for taking away the heat. This is also possible. That means screw compressors can handle a mixture of liquid as well as vapor, which is not possible in reciprocating type of compressors. Okay, so this is another advantage of screw type compressor. The capacity is normally controlled down to 10% of full load with the help of a slide valve. So, you can get really a smooth capacity control in this type of a compressor using a slide valve. And what does the slide valve do? The slide valve, as the slide valve is opened, some amount of suction refrigerant escapes to the suction side without being compressed. Basically, you can shift the point at which the compression begins, thereby you can control the mass flow rate of compressed refrigerant. That is how you control the capacity, and as I mentioned, the capacity can be reduced right from 100% to 10% of full load in various steps. For a given built-in volume ratio, the efficiency reaches a peak at a particular optimum pressure ratio, as I have already mentioned. Let me show this. This is a typical performance characteristic of a twin screw compressor. So, as you can see that here the compression efficiency, this is the compression efficiency is plotted against pressure ratio PD by PS for different built-in volume ratios. Okay. So, VB is your built-in volume ratio, and it is increasing in this direction. And for a given built-in volume ratio, for example, let us take this one. For a given built-in volume ratio, the compression efficiency increases as the pressure ratio increases and it reaches a peak. That means, for this particular compressor, efficiency is maximum at an optimum compression ratio. This is your PD by PS optimum. Okay. So, if you design your compressor in such a way that at design point this is the compressor operates at this point, then you get the maximum efficiency. However, at off design conditions the compression ratio can go this side or this side. So, that means the efficiency will reduce when you move away from this peak point. Okay. And you can also see that as the built-in volume ratio is varying, the optimum pressure ratio at which the peak efficiency occurs also shifts. Okay. The compression efficiency drops when the system operates at off design conditions. However, when operated at the optimum pressure ratio, the efficiency is much higher than other types of compressors. You can get a compression efficiency as high as 70% or more. As the rotor rotates at high speeds, screw compressors can handle fairly large amounts of refrigerant flow rates compared to other positive displacement type compressors. Screw compressors are available currently in the capacity range of 70 to 4600 kilowatts. So, normally screw compressors compete with high capacity reciprocating compressors and low capacity centrifugal compressor. That means they occupy the space in between reciprocating compressors and the centrifugal compressors. Okay. They are available for a wide variety of refrigerants and applications. Compared to reciprocating compressors, screw compressors are balanced and hence do not suffer from vibration problems. Since you are not converting rotary motion into reciprocating motion in any of these rotary compressors, not only screw compressor, also in fixed vane and multiple vane type of compressors, these rotary type of positive displacement type compressors offer less vibration and less noise compared to reciprocating type of compressors. Okay, that is, they are better balanced. And screw compressors are rugged and are more reliable than reciprocating compressors. It is shown that they can run for continuously for 30,000 to 40,000 hours between major overhauls. This is cited as one of the principal advantages of screw compressor. That means between major overhauls the running time can be as high as 30,000 to 40,000 hours. Okay. So, they really do not require any major overhauling in between. Right. So, this is very beneficial as far as the plant running is concerned. Okay. Now, let us briefly look at the other type of screw compressor, that is single screw compressor. This single screw compressor consists of a single helical screw and two planet wheels or gate rotors. The helical screw is housed in a cylindrical casing with suction port at one end and discharge port at the other end. Suction and compression are obtained as the screw and gate rotors unmesh and mesh. The high and low pressure regions in the cylinder casing are separated by the gate rotors. Okay, so let me show the schematic of single screw compressor. So, as I said, you have a single helical screw. This is the screw. This is the one, this is driven by a motor and it rotates in this direction, and it also consists of two gate rotors or planet wheels. Okay, you have one gate rotor on this side, one gate rotor on this side, and this helical screw is kept in a cylindrical housing. Okay, and this is the suction port and this is the discharge port. So, suction gas enters like this. Okay, and the space between this region and the region between the planet wheels and the screw is occupied by the suction gas, and as this rotates in this direction, the suction gas will be carried away and as it passes the gate rotor it undergoes compression, and when it reaches this point its pressure would have been equal to or slightly higher than the condensing pressure, so that discharge will take place through the discharge port. Okay. So, the gate rotor basically seals the high pressure region from the low pressure region. Normally the screws are metallic and the gate rotors are plastic. That means they are made of plastic materials, and helical screw is made of metallic material. The screw, as I said, is driven by an electric motor, and the gate rotors are normally made of plastic materials. A small power is required to rotate the gate rotors, as the frictional losses between the metallic screw and the plastic gate rotor is very small. Similar to twin screw, lubrication, sealing and compressor cooling is achieved by injecting lubricating oil into the compressor. Once you inject lubricating oil, obviously you require an oil separator, oil cooler and oil pump to circulate the lubricating oil and to reject the heat of compression. So, this is the typical characteristics of single screw and twin screw type of compressors. As I said, these compressors can handle a mixture of vapor and liquid, and in fact instead of using lubricating oil you can as well use refrigerant liquid itself for sealing and for carrying away the heat of compression. Okay. Now, let us look at another very important type of positive displacement type of compressor. This is known as scroll compressor. Scroll compressor is sometimes called as an orbital compressor. Let me describe the working principle. Scroll compressors are orbital motion positive displacement type compressors, in which suction and compression is obtained by using two mating spiral shaped scroll members, one fixed and the other orbiting. That means basically what we have here is two spiral shaped scroll members, and one of them is fixed and the other one is orbiting. Okay, so let me just show a downloaded clip. Yeah, you can see this is downloaded from the internet, and it is made by the Southern Illinois University, and this picture here shows for example here this is one spiral member and this is the other spiral member. One is fixed, the blue one is fixed and the red one is orbiting. As it orbits, suction, compression and discharge takes place. Okay. So, you can see that as the red one is orbiting, you see that it is not rotating, it is orbiting. Okay. That is why you call it as orbital compressor, and the blue one is fixed. Okay. So, the gap between the blue and red scroll members is varying continuously. This is what gives rise to suction and compression. Okay. And an anti-rotation coupling is used to maintain a fixed angular relation of 180 degrees between the fixed and orbiting scrolls. This is not shown in the picture, but an anti-rotation coupling is essential. It has to maintain a 180 degree phase difference between the fixed and orbiting scrolls. Once again, let me show how it works. Okay. So, this picture here shows the working principle of scroll type compressor. So, what is shown here is suction, compression and discharge. So, this blue in this particular this blue region is the suction gas. So, you can see that the space between the two scrolls is fixed by the suction gas, and as the orbiting scroll rotates, this suction gas is moved from this periphery to the inner this thing. Okay. So, this is now this gas has occupied this region, and at this point this volume is less than the volume at this condition. Okay. So, some compression has taken place, and with further rotation the gas is moved to the center. Okay, this red portion. At this point the compression is completed and the pressure equals or slightly exceeds the condenser pressure. So, the discharge valve is opened and discharge takes place. So, you have the three steps: suction, discharge and compression, and how the gas is moved from the periphery to the inner eye. Okay. So, normally you have the suction port at the outside, I mean at the periphery, and the discharge port at the center. Okay. So, this is the working principle of a scroll type compressor. And each scroll member is open at one end and bound by a base plate at the other end. So, let me show this. Okay, so this is picture is not very clear, but here what is shown here is this is the rotating scroll and this is the fixed scroll, and this is the scroll member. Okay, again this is the scroll member, and this is open on this side, this is the open end, and this is the open end. Okay, and this is the base plate, and this side also you have a base plate. Okay, so basically when you assemble it, this goes and sits inside, and this will be orbiting in this direction. Okay. This picture shows the photograph from the side view and from the front view, and you can see here the two scroll members. One is the violet colored one, this is one, and this is the other one. Okay, the violet colored one is the fixed one, and this one will be rotating. Okay, and you can see that one side it is open, and this is the base plate, right, and you have another base plate here. So, another base plate is there. Okay. This shows the cut view of a commercial hermetic scroll compressor. So, you can see the various key components in this one. Since this is a hermetic type of compressor, the motor is also kept inside the same housing. So, you have the discharge plenum, as I said, as I explained, you have the discharge plenum here. Discharge takes place through this, okay, and suction takes place in this manner, okay, and you have the motor here, and the scrolls are kept here, fixed and orbiting scrolls, and various other components. Okay. Scroll compressors are used in small capacity 3 to 50 kilowatt refrigeration, air conditioning and heat pump applications. In fact, they are becoming quite popular in this range because they offer many advantages. They are normally hermetic type. Compressor capacity is normally controlled by variable speed inverter drives. Basically what is done is the frequency of the motor is varied. Okay, the frequency can be varied from as low as 15 hertz to right up to 150 hertz. Okay, that means you can get a very fine capacity control by controlling the speed of the motor. Okay, this is a popular method of controlling the capacity of scroll type of compressors. Okay. Of course, one major problem with this scroll type of compressor is the manufacturing. Manufacturing is relatively difficult due to the need for very close tolerances between the fixed and orbiting scroll members. Scroll compressors offer several advantages. First advantage is large suction and discharge ports reduce pressure losses during suction and discharge. So, there will be higher volumetric efficiency, and physical separation of suction and compression reduce heat transfer to suction gas, leading to high volumetric efficiency. This is another typical advantage of this type of compressor. As you can see here, suction is taking place here, so simultaneously discharge will be taking place somewhere here. Okay. So, for example, this is the hottest hot gas, let us say, and this is your cold gas. Since they are physically separated, heat transfer from the hot gas to the cold gas is minimized. As a result, the density of the suction gas will not drop very much, unlike in reciprocating compressor. As a result, the volumetric efficiency will be high. In addition, of course, the re-expansion losses are also quite less in this one, and the flatter capacity versus outdoor temperature curves. And another advantage is that higher compression efficiency, low noise and vibration compared to reciprocating compressors. They are compact with minimum number of moving parts. So, because of these advantages, scroll compressors are finding applications in many air conditioners and all. In fact, the scroll compressor is pioneered by Japanese, and they are becoming very popular in packaged air conditioners and small refrigeration systems. Okay. Now, let me summarize what we have learned in this lesson. In this lecture, we discussed the working principle and characteristics of rolling piston type compressors, multiple vane type compressor, screw type compressor, both single screw and twin screw type compressors, and scroll type compressors. There are also other positive displacement type of compressor, what is known as the trochoidal type of compressor, but this is still not very popular, not still under development. Okay. Whereas these 4 types have already been developed and they are available commercially. Okay. And this completes the discussion on positive displacement type of compressor. As you can see, we have spent more time on the reciprocating type because they are the real workhorse of the refrigeration industry. However, the other positive displacement types are also becoming popular. Okay, since this is a basic course, we have not discussed these compressors in detail. And in the next lecture, I will discuss rotodynamic type of compressors, mainly centrifugal compressor. Okay. So, before I stop here, I would like to give a homework problem. Let me read the homework problem. The problem is like this: a refrigerant has a molecular weight of 64.06 kg per kilomole and a specific heat ratio Cp by Cv of 1.26. If the compression ratio Pd by Pe is 3.119 and the refrigerating effect is 322 kilojoule per kg at an evaporating temperature of 4.5 degrees centigrade, find A, the theoretical COP, B, the enthalpy change of the refrigerant due to compression, and C, temperature of the refrigerant at the exit of the compressor for the following cases. So, what is given here is the molecular weight, specific heat ratio, compression ratio, refrigeration effect and the evaporating temperature. Okay, and we have to find out the COP, enthalpy change and the discharge temperature. Okay, and what are the different cases for which we have to find these values? First one is reversible adiabatic compression. Second one is reversible polytropic compression with polytropic index of 1.22. The third is irreversible adiabatic compression with index of 1.3. And you can assume no superheating and the refrigerant to behave as a perfect gas and the specific heats to be constant. Take the value of the universal gas constant as 8.314 kilojoule per kilomole Kelvin. Let me give a hint. You have to as I have already mentioned, you have to assume the refrigerant to be a perfect gas. So, you have to apply PV to the power of n is constant and you also can apply PV is equal to RT. Okay, these two equations you will be applying. And for the reversible cases, you have to you can find out the work input to the compressor by integrating integral VdP, okay, from the suction pressure to the discharge pressure. Whereas for irreversible case, you cannot use the integral VdP for finding the work of compression because you do not know the process path. Okay, so what you have to do for the irreversible cases, you have to find out the discharge temperature from the two equation PV to the power of n is constant and PV is equal to RT, and then apply energy balance across the compressor and find out the work input, which is nothing but mass flow rate into enthalpy rise across the compressor. Okay, so that will give you the work of compression for the irreversible case. Whereas for the other two cases, you can find out work input from integral VdP. Okay, I will give you the answers to this problem in the next lecture. Thank you. Welcome back. In this lecture, I shall discuss centrifugal compressors. So, the specific objectives of this particular lecture are to describe the working principle and constructional features of centrifugal compressors, present an analysis of steady flow compressors and define polytropic efficiency, establish relationship between power input, pressure rise and tip speed. So, at the end of this lesson, you should be able to explain the working principle of centrifugal compressors, carry out thermodynamic analysis of steady flow compressors, and establish relationship between impeller speed, diameter and power input and pressure rise. Let me give a brief introduction. As you know, centrifugal compressors, also known as turbo compressors, belong to the rotodynamic type. In these compressors, the required pressure rise takes place due to the continuous conversion of angular momentum imparted to the refrigerant vapor by a high speed impeller into static pressure. Unlike reciprocating compressors, centrifugal compressors are steady flow devices, hence they are subjected to less vibration and noise. Now let me explain the constructional features of a centrifugal compressor. You can see the side view and the front view of a centrifugal compressor. Refrigerant enters like this, and this portion, if you look at this, this is the inlet, refrigerant inlet. This is also known as eye of the impeller. So refrigerant enters like this and then takes a 90 degrees turn and enters into the blade passages of the impeller. These are the impeller blades. So the refrigerant flows through the passages provided by these impeller blades, and these impeller blades will be rotating at very high speed, as a result of which momentum will be imparted to the refrigerant when it comes in contact with the impeller blades. So from the impeller it enters into a region called diffuser, that is 4. Okay. In the diffuser, conversion of velocity pressure into static pressure takes place, as a result of which its velocity reduces and the refrigerant pressure increases. And from the diffuser it enters into a volute casing. You can see that the volute casing has uniformly gradually increasing area. So as the refrigerant flows through the volute casing, its velocity reduces gradually and velocity is converted into static pressure. So finally the refrigerant comes out of the compressor at high pressure. So once again you can see the how the refrigerant flow is taking place and different parts. As I said, part 1 is the refrigerant inlet, and part 2 is the impeller. 3 is the refrigerant passages, so these are the refrigerant passages, and 4 is the vaneless diffuser, this is the vaneless diffuser, and 5 is the volute casing, and 6 is the refrigerant discharge. Now let me explain the working principle. Low pressure refrigerant enters the compressor through the eye of the impeller. Eye of the impeller is nothing but the inlet of the impeller. From the eye, the refrigerant enters the flow passages formed by the impeller blades, which rotate at very high speed. That means the impeller will be rotating at very high speed. As the refrigerant flows through the passages towards the tip of the impeller, its angular momentum and static pressure increase. From the tip of the impeller, the refrigerant flows into a stationary diffuser. In the diffuser, the refrigerant is decelerated, and as a result the velocity pressure drop is converted into static pressure rise, thus increasing the static pressure further. The vapor from the diffuser enters the volute casing, where further conversion of velocity into static pressure takes place due to the divergent shape of the volute. Finally, the pressurized refrigerant leaves the compressor from the volute casing. So this is the working principle of a centrifugal compressor. This is different from your positive displacement type of compressor, which are unsteady flow devices. Now let me explain the physics. The gain in momentum is due to the transfer of momentum from the high speed impeller blades to the refrigerant confined between the blade passages. The increase in static pressure is due to the self compression caused by the centrifugal action. I will explain what it is. And the static pressure produced in the impeller is equal to the static head, which would be produced by an equivalent gravitational column. As you can see that as a